Madam, இங்க டீ
Namni
Hello.
Sir, unable to hear anything from the group. Hello, sir.
Good morning, participants. The session is going to start. Sir, shall we start the session?
Yes, ma'am. Yes, ma'am. Please.
Okay, then. A very good morning to one and all present here. Every morning brings us new thoughts, new words, new strength, and endless possibilities. So, to brighten us our morning, here comes the workshop on dimensions of control systems. On behalf of SRM TRPEC Engineering College, I welcome you all for the 2 days national level workshop on dimensions of control systems organized by the Department of Electrical and Electronics Engineering in association with Institutions Innovation Council. Now I request Dr. P. Ilangovan, Head of the Department, to deliver the welcome address. Sir, please.
Thank you, ma'am. A very good morning to one and all. On behalf of organizing team of this national level workshop on dimensions of control system, I take immense pleasure to welcome our respected principal sir, Dr. B. Ganesh Babu, who facilitated a very good platform to organize this workshop. It has not been an easy transition for any of us, but your leadership and positive attitude have helped us to pull through this workshop. Welcome, sir. Next, I would like to welcome our Vice Principal, sir, Dr. Ramasubramaniam, who joined hands with us along with his department to execute this workshop. Welcome, sir. Then I extend a very sincere warm welcome to our speaker of today's session, Dr.M.Arul Prasanna, Associate Professor, Department of PSNA College of Engineering and Technology, who accepted our invitation without any hesitation for the second time for this workshop. Welcome, sir. Then I would like to welcome all the participants, my dear students and my faculty friends, without whom this workshop is not at all possible. Once again, I welcome you all for this wonderful session. Thank you.
Thank you, sir. Now I request Dr. B. Ganesh Babu, Principal of SRM TRPEC Engineering College, to facilitate the gathering. Sir, please.
Thank you, ma'am. A very good morning, one and all present here. It is really immense pleasure to participate in this workshop. In particular, Dr.M.Arul Prasanna, I would like to welcome you for our SRM Engineering College workshop.
Thank you, sir. Thank you, sir.
After so long time, I am seeing you, sir.
Yes, sir. I also remember you.
Yes, it makes me a great pleasure for me. And it is a very good effort taken by Electrical and Electronics Engineering Department and participate, go hand with the EC department also. I must congratulate all these coordinators and all the professors. Those are all taking all the efforts to make this session in this level. And I must appreciate the participants. Those are all eagerly awaiting, even after a postponement also, they are eagerly coming to this session and supporting for the workshop. I hope really it will be a wonderful session. In particular, in this era of automation, that is Industry 4.0 era, the automation is going to lead the industries. So at this juncture, this control system in industrial automation is it's a really well worth topic. I hope everyone will get benefited out of it. You can have a lot of takeaway points from this workshop. Once again, I wish you all the best for a wonderful opportunity, what you are having in your mind. And I must appreciate the HOD EEE and coordinator Tony Raj sir for taking a lot of effort. And one more thing is, this particular workshop is also coordinated by the institution's Innovation Council. That must also be recorded here. So with all these positive minds making a very good platform for learning, so I hope it will be a wonderful session. I wish you all the best. Thank you.
Thank you, sir. So it gives me a great pleasure to introduce our chief guest of this workshop, Dr.M.Arul Prasanna. He has completed his BE in Electrical and Electronics Engineering in 2016 and CG in Power Electronics and Drives in 2008 and a doctorate in Power Electronics and Drives in 2015 from Anna University, Chennai. He has a teaching experience of 11 years and he is currently working as an associate professor in Electrical and Electronic Engineering in PSNA College of Engineering and Technology, Dindigul. He has published 18 papers in reputed journals. He is also one of the reviewer in IEEE Transactions on Power Electronics, Electric Power Components and Systems, IETE Journal of Research and Advances in Mechanical Engineering. He is guiding 5 PhD scholars under his supervision. Once again, I welcome you for this workshop, sir.
Thank you, ma'am.
Education is the most powerful weapon which can be used to change the world. I request all the participants to utilize this session effectively. Now the session is handed over to our resource person, Dr.Arul Prasanna, sir. Sir, please.
Yes, ma'am. Yeah, very good morning to all. First of all, I thank the SRM TRP management for giving me an opportunity to deliver a webinar on role of control system in industrial automation. Okay, I especially thank the principal, the vice principal, and the HOD of EEE, and the staff coordinators Tony Gilbert, and then Kritika and Kriba ma'am. Okay, so let us start with the session. See, automation is not a thing that is just evolved simply in the right time. Okay, it has a history of sequences that happen in the past timings, depending upon the scarcity in manpower and like that. This scarcity make the scientists to research and work on these equipments to get them automated. Okay, so automation simply covers the applications that ranges from simple our household thermostats that controlling our boilers or geysers, and to a large size industrial control system. Okay, so when you are talking about a large size industrial control system, that may implies that it involves more number of inputs and outputs. Okay, so inputs might be coming from several sensors and several transducers like that, whereas the output are those appliances what we are going to get control. Okay, so when you are talking about an industrial automation, it is just a huge thing. Okay, it is just some 100 times or 200 times magnified thing when you are compared to a simple level automation. Okay, so in terms of complexity, we can range the automation as a simple on-off control. Right, so if you are providing an automation for a simple on-off control process, then it is called comes under the small level automation. Okay, so when you are going for a multivariable, because if you are going to process some 2 or more number of inputs that are having some different terminology or different parameterizations, and if you are processing it into a single controller, means then they go for a multivariable high level algorithms. Because the algorithms will analyze which input signal is coming from which type of sensor, and that process is to be converted into understandable form for your controller, and then your controller will process the input signal, then it will provide an output depending upon your programming. Okay, so always your automation or automation system means it will have an input system and then a central CPU part, that is a controller part, and then an output section. Okay, so that output section and input section are simply isolated from each other. Okay, they do not have any physical wiring or physical connection between them. Only they will able to get connected through the CPU, that is your controller. Okay, so this controller has a different level of history. Okay, so starting from a simple relay to nowadays we are using some PLCs and SCADA like this. Okay, so this controller is going to be the part that is going to get the industry into industry 4.0 up to now. Okay, so 4.0 is nothing but the revolution that is happening in the industry now, that is that tends the automation process to be get their own decision on scanning the things what is happening in the process industries. Okay, so let us start with the first automation equipment that is designed. It means in 1771, Richard Arkwright invented the first fully automated spinning mill. Okay, see here you have seen have a picture over here. This is what a spinning mill system, which is driven by a wheel, right? A water frame wheel. So this wheel is getting power from the water driven turbine. Okay, so this shaft is connected to a water turbine, and that turbine will make this one to rotate. Because with the help of this revolution, we are making our spinning process to get success. Okay, so later in 1785, Oliver Evans, so he is the only man who have completed the entire automation plant in a full-fledged form. Okay, so he is making his first complete automated industrial process for a flour mill. Okay, so in 1771 to 1785, we have a variation in the automation history. Okay, so these two fellows lay the way for automation, and they find the things that is going to get evolved for the next generation people. Okay, so before getting into the automation, let us know what are the things that are utilized in the automation system. Okay, so simply calling it as a automation component, you might know the relays. Okay, so relays are nothing but as switches, right? Or otherwise you can call it as a controllable switches. Okay, so in technically, if you want to make this relay as a wording, means you can call it as a logical switch. Okay, so this logical switch or control switch has its variation from the normal switch in terms of its operation. Okay, so when you are comparing a normal switch operation, whether it is a toggle switch or a push button, we can have the output power to get connected to the input power, output load to get connected to the input power. We need to go for a variation in the toggle, right? So if you make the switch from on to off, the power supply will get cut off, right? And similarly from off to on, the power supply will be connected to the load. Okay, so this is happening in the presence of a human intervention. Okay, so when you are trying to make this one as an automated one, we need a switch called as the relay. Okay, so if you are not present over there and you are going to give some inputs through some power supply, and depending upon that power supply, your output is just to be going to be get turned on or turned off, means you need a relay for doing this. Okay, so let us see what is a basic relay. See, the basic relay is having some 5 terminals. Okay, so this relay in electronic shops we can call it as we can ask them for sugar cube relay, right? Since it looks like a sugar cube, right? So the sugar cube relays are having some 5 terminals, namely the coil, right? Coil, that is where your energized magnetic field is going to be generated, and this belongs to terminal 1 and 2, right? 1 coil and 2 coil. Okay, these 2 terminals will have a coil in between them. Okay, and then you are having another one terminal called common, right? And 2 more remaining terminals are called as normally closed and normally open terminals, right? So we can call it as in short form as NC and NO. Okay, so hereafter we will make it as NC and NO only, right? So what happens inside the relay? See here, this is what the internal circuit that is provided inside the relay. Here we are having a coil, right, between terminal 1 and 2, and you have a output contacts like NC contact and NO contact, and then the common contact. Okay, so these 3 terminals are called as contacts, and these 2 terminals are called as coil. So a relay is consisting of both coils and contacts. Okay, so in which way are you going to use the coils and contact, that may vary depending upon your program. Okay, so what this relay will do, whenever you are getting whenever you want to get an output to get turned on for a logical operation, you just provide the power supply to the coil 1 and 2. For example, if this relay is meant for some 5 volt, see in this picture it is mentioned that as 5 volt DC. Okay, so whenever you are giving 5 volt here, this coil will get energized, right? Once this coil is energized, what happens? Here we are having a common terminal, and in this common terminal a contact is connected, right? And this contact is attached to a spring attachment, right? So once your magnetic coil is get energized, the field generated through this magnetic coil attract this contact. Okay, so initially this common terminal is always connected to normally closed terminal. Okay, whenever this magnetizing coil is get energized, this contact will move from normally closed to normally open. Okay, once you remove the 5 volt here, then again it will reverse back to normally closed position because it is attached to a spring, right? So due to the tension in the spring, it will automatically get attracted to normally closed terminal. So that's why it is called as normally closed. So whatever the voltage you have given in your common terminal, that will be available in NC. Okay, and similarly, whenever you are you want to have this common terminal voltage available to be get available in normally open, you just energize this coil. So in this way, you can make the relay to work for our particular application. Okay, so once the coil is energized, this contact is this common contact is attracted towards normally open, right? And it will get connected to the normally open terminal. And if you connected the phase of the power supply or positive terminal of the power supply to the common terminal, that will be available in your normally open when the coil is energized. Okay, and the replica will be happening when your voltages get removed from your coil. Okay, so let us get this one in with better understanding. See here, this is the thing what is happening. See, this is the push button we are using to make this coil get energized. Okay, so it is connected to a battery. So once this push button is pressed, the magnetic coil will get magnetized, right? And this contact is now get attracted. Okay, so once this attraction happens, see, it is connected to a lever of movable contact. So this is normally NC and this is NO. Okay, so when you are connecting your output load to the NO terminal, when you are pressing the switch, the lamp is glowing. Okay, if you are connecting your lamp terminal to your NC contact, then when you are not pressing the switch, the lamp will be glowing. Okay, so we can understand this one with the next diagram. So we are having some 2 switches, one with connected to NO and another one with connected with NC. Okay, so see here, this is the voltage buildup, and once the switch is pressed, the contact is moved here. Once the switch is released, the contact is immediately retracted to the NC terminal and this lamp is going to be get glow. Okay, so this can be understandable better in this diagram. See, once this is pressed, one of your lamp is get glow. Once the push button is released, another lamp is glowing. Okay, so we can have a sequential turn on and turn off of your loads depending upon the push button logic here. Okay, so this is somewhat you might know before getting into the real automation process. Okay, because understanding the basic operation of a relay is very much helpful in programming your PLC. Okay, because PLC is basically a relay based controller that is going to work with this combination of contact coils and other things. Okay, so this is a history how your automation control system evolves in the process control plants. Okay, so the first option to do our process control is nothing but a manual control. Okay, we know that, right? So any process can be done manually, but it involves some more amount of manpower and knowledge also. Okay, so the second option available is nothing but the hardwired relay logic. Okay, so what we have seen with the relay is nothing but the hardwired relay logic. So a simple process control plant can be automated with the help of a simple relays itself, right? So what is the drawback then? Because when you are going for any automation, we need some automation devices. So relay is one of the device which is also somewhat low cost, right? And once we program a particular process with relays means then the total process project ammo, project design cost and everything will be going to be a simplified one. But the thing is where you are facing the error means while we are going for any maintenance problem or when you are going for upgradation in your process plant, then this hardware relay logic will not be a valid one. Okay, so let us take a simple example. For example, we are having a washing machine to be get automated, right? We are going to design a washing machine, and in that washing machine we are having some 3-step of process involved. Okay, for let us have a first process with some rinsing, soaking process, and then washing, and then some rinsing. Okay, so each process will involve some 5 number of relays, means totally some 15 relays we need for 3 process to get completed. Okay, so each relay will have some 5 terminals, so 15 into 5 will have some 60 terminals that is going to be involved, and in addition we are having some power supply terminals and other control terminals switches like that. So totally some
presentation, sir.
presentation. Wait, sir. Sir, 1 second, sir. Google Meet got resetted. So wait for a minute. I have got a network problem in my PC. Actually, my network adapter in my PC got resetted. It's restarting now. Wait for a minute.
Yeah, okay, sir.
Yeah, thank you. Sorry for the inconvenience.
Yeah, no problem, sir. No,
Yeah.
no problem, sir. No problem, sir. Please proceed.
Yeah. So
Sorry, sir. Thank you.
the second option available for our control process to get automated is nothing but a hardwired relay logic, right? So when you are talking about the relays, clearly it will involve some 5 terminals for a simple basic relay. And when you are going for the process to get evaluators with the help of some 20 or 30 relays, means imagine about the thing, how many terminals that is going to involve and how many wires that are going to get involved in that particular process. Okay. So once we design a plan for a relay process, and we have make all the relays to get connected, and the circuitry is okay, and we have checked out it, and everything is working nice. Okay, and we led the project to the customer, and he is also working with that project nicely. Okay, and after some time, if he faces some error, right? So there is some malfunctioning in the relays and in the latching process that is happening inside the relays, right? So malfunction is happening means once even who designed that particular project, he, going for the troubleshooting means he will facing the debugging problem. Okay, because he can't go for all the 20, 30 or 40 terminals to get individually evaluated for a simple process. Okay, so think about an industry which is having some more number of 500 to 1,000 number of inputs and outputs. And if you are doing a particular project with the help of relays, means then 500 to 1,000 wires that is involved in that particular project. And if there is any error happening in that particular thing, means we can't able to find which relay is going off and which relay is malfunctioning like that. Okay, and the thing is we have to go for troubleshooting for each and every relay. Then only you'll be able to find the problem, and then we can go for the or the working of your particular project back again. Okay, but the thing that is happening in between this will surely make the customer to have some production loss. Okay, so because in industry money is calculated in terms of time, right? So the time is the main thing that is that predicts the profit of a particular industry. Okay, so how much time you are taking for troubleshooting that particular error, that depends upon the technology we are using. Okay, so this hardware relay logic faces so many drawbacks like troubleshooting of error and maintenance cost, because when your relays are continuously get latched for a high current rating, the acid deposition in that particular contact will make the relay to not working. Okay, so these are some of the problems that hardware relay logics methodology faces in the industry, so that they have gone for the option 3, right? So what is option 3? Option 3 is nothing but the dedicated electronic control boards. Okay, nothing but our PCB, right? So in PCB we are having just ICs. So the same relay logics, that is your logical operations, can be done through our ICs, right? So we are having AND gate, OR gate, NOR gate, XOR, all the gate ICs are available, and they are so much smaller in size. And the same thing what you have done with your hardware relay logic, we can establish the same process control using this dedicated electronic control board itself. Okay, but what is the drawback in electronic control boards? So once your process is defined, you have to design, you have to go for the design of a particular PCB, and that PCB is dedicated for only for that particular process. Okay, so a simple process you have defined, and you have developed a board for that particular simple process, means that board is dedicated for that particular simple process alone. Okay, you can't get any small complexity or any can't add any additional features in that dedicated board. So if you want to go for any upgradation in your project, then this dedicated board will not be a valid one. Okay, you have to go for a new board one. So in industry, upgradation is happening every day. Okay, and moreover, the transition from one particular logic to another logic is also happening. Okay, so when you are having a dedicated electronic board for that such particular processes, you have to go for continuous design of these PCBs. Okay, so you have that is versions, right? So version 1, version 2, version 3, like that. You have to go for this PCB designing and manufacturing and fabrication. So what about the cost involved for this such production of this PCB from design level to a fabrication level. Okay, so when you are going for any upgradation in your process, this dedicated electronic control board will not be valid for that one. Okay, so that will be overcome by our fourth option, what is nothing but our programmable logical controller. Okay, that is the PLC. Okay, so PLC is also a controller, right? It is also a microcontroller. But the thing is, it is somewhat flexible when compared to all the three options what is available in the history. Okay, so why we are going for PLC? That is the thing we are having in mind when you are comparing with the other three options, right? So see here, this is what the hardware relay logic circuits will look like. Okay, so here you are having some AND and OR logics. See here, parallel switches, series switches, right? So with the help of these parallel switches and series switches, these are nothing but the contacts of your relays, right? And these are nothing but the output terminals, right? So these contacts and terminals are get connected in such a fashion through wirings, right? So this hardware relay logic will look like this. See, when you are having relays in your, when you are using relays in your circuitry, it will involve this such
Sir,
amount of
excuse me,
wirings.
sir. We can't see any screen, sir. I'm not able to see any screen, sir.
Yeah, it's actually visible.
It's not visible, sir. The screen is not visible. It's whole fully black.
Sir, it is visible.
Yeah, it is visible for me also.
Yeah, it is visible. You
Just
kindly
ping-
ping sir link, madam.
If you are pinning others name means it will not be visible. Yeah. So next thing is the electronic logic gates, right? So that is our PCB. So instead of your logical relays, we are using logical ICs. Okay. So here AND IC is used for performing AND operation, and we have a comparators, and this is our output, right? So here also it involves some wirings, but it is in terms of traces, that is in PCB boards. Okay. So what electronic logic gates will have? See, when you are having a electronic logic gates used in your circuitry means you will be having a board like this. Okay, so it will have a dedicated control boards, and that control board will be able to process for that particular programming alone. Okay, we can't make any alterations in your programming, and inside the programming, just with the logical things, we can make some small changes. For example, some time values and counting values like that we can change, but we can't go for any additional number of inputs or outputs get added to your available electronic boards. Okay, so this will be overcome by our PLC. Okay, so because PLC will have a capability of getting add-on units in addition to your available control. Okay, so if you are not satisfied with your available inputs and output means, you can go for some additional number of inputs and outputs with the help of your add-on units. Okay, so these add-on units will be available in the market depending upon the module you have already or CPU already you are having, right? So you have to select that particular add-on units and get added with your available controller means the same CPU will take care of this additional add-on units also. Okay, so you have just to increase your input and outputs with a minimal cost. Okay, if your programming, if your process is getting upgraded, means you just include some additional add-ons, then that is enough for that. And you can include some additional programming lines also. So programming is done through software, so no need of any hardware components required for programming, right? Whereas this additional add-on units will helpful in getting your inputs and the outputs get connected when you are in a demand of additional number of inputs and outputs get added to your system. Okay. So this is a basic PLC which looks like. So this is what the PLC we are having in our PSNA Siemens Center of Excellence. That is S7 SIMATIC S7 1200. So this is a Siemens make PLC, right? And each PLC will have two set of units, that is input unit and then an output unit. Okay. So these input units are called as digital IOs, DI, and whereas these output terminals are segregated as DOs, that is digital outputs. Okay, so DI DOs. Along with this DI DO, some of the modules will have some analog input and outputs also. Okay, so that will come under the category of analog processing PLCs. So that will have additional terminologies for inputs and outputs as AI and AO. Okay, AI stands for analog inputs and AO stands for analog outputs. Okay, so what are all the capabilities of a PLC? See, let us start with a logic control. So a basic PLC will have able to perform any type of logical operation. Okay, if the logic is correct, right? If it is logically possible, we can make through a PLC. Okay, that is the first criteria, right? Possible logically, if it is possible means you can do it, right? And next thing is it is having inbuilt timers. So when you are having a hardwired relay logic or a dedicated control board, we are having a dedicated a timer circuit for that. And if you want to make any changes in that particular timer circuit, means we have to go for replacing the components or fabricating a new board. Okay, but in your PLC that is not needed because it is having a inbuilt timers, and those timers are also called as software timers. Okay, so any change in the timing value will be reflected in the software, right? No additional hardware variation is happening inside it. Okay, so only the software that is going to be helpful for changing the timers, timing values in your timers, and similarly for your counters also. Okay, so you have inbuilt counters. So each PLC will come with around 256 timers and counters. Okay, defaulting. So even for a big program, we are just using some up to 10 to 20 timers. Okay, so but the PLC has a capability of running some 256 timers at a time. So think about the capability of a PLC, right? 256 timers they have given as a provision for you means 256 timers can be run at a time by a PLC. Okay, in parallel, right? So this is what a beautiful thing when compared to our normal circuitries and hardware logics. Okay, and next thing is processing of an analog signal. So PLC have a capability of processing analog signal if the PLC is provided with a analog processing channel. Okay, so the modules of PLCs are available only with digital and digital with analog and only analog. Okay, so which category you want to have for your particular project, you can select. Okay, if your project is not having any analog input and outputs means you can just go for a simple digital IO PLC, right? So digital IO means DI/DOs. Okay, so that will be of very low cost, right? And when you are going for a project which is happening, going to handle some analog values means you have to select a PLC with both digital and analog. Okay, so when you are selecting a PLC with analog means surely the PLC is having an analog channel, right, through which the analog signals that are directly get from the sensors are going to be get converted into digital form. Then only it is given as an input to your PLC controller, because PLC controller it is a digital, right? It is purely a digital controller, but it can able to process analog thing through a analog signal processor, right? And next thing is it is having PID controller, right? So when you are going for any process for a temperature control process means we are going to control some room temperature with the help of a temperature sensor means we have to use this PID controller. Right, so this PID, this KP, KI, and KD, these values are embedded into your PID controller unit of your PLC, and depending upon the variation in your temperature, the curves are automatically defined by the PLC PID controller, and the temperature is maintained in a normal settling state. Okay, and arithmetic function. So already we know that PLC is also having a controller. So each controller will have a ALU inside it. So any arithmetic functions can be performed in your PLC. So because arithmetic functions means it involves addition, subtraction, multiplication, division, summation, negation, like that. Okay. So any arithmetic process can be done through a PLC. So this will be helpful in industries, those who are doing batch processing. Okay. So they want to count the end of the day product count, how much beverage bottles are manufactured today, or how much soaps are manufactured today. Like that, if they want some end of day count for each process means they will put a sensor and give it to a counter. That counter will count all the values and store it in your PLC memory. Okay. Once a particular level is reached, if you want to make your machine to turn on or turn off, that decision will be taken inside your intelligent program. Okay, and similarly communication. So So far, your hardwired relay logic and dedicated control boards, those are not having any provision for live communication with your CPU. Okay, so in your dedicated control board, we are having some controller IC, means we have to make that controller IC take out of your board and put it in a development environment, right? And there only you are able to program it or communicate with that particular control IC. Okay, whereas in PLC, we can have a communication cable through which we can directly communicate with your CPU, even the program is in live running condition. Okay, so that will offer you to understand what is exactly happening inside the PLC, and if you want to make any change, that will be reflected in the next CPU cycle. You just change the program and just upload it, means it will be reflected in the next CPU cycle itself. Okay, without turning off your PLC or without going for any shutdown process, you can lively update all your upgradation that is happening inside your program. Okay, and next thing is a HMI operator panel, right? So when you are designing a particular project and you think of that PLC is somewhat a high-end controller that can be programmed only by skilled persons like that. Okay, no problem. The programming can be done by a skilled person, but the process can be controlled by a normal layman. Okay, so that is made possible with the help of this controller panel, HMI controller panel. So what is HMI? HMI is nothing but human machine interface. Okay, so what this human machine interface will do? So the programmer or the skilled programmer, what he will do? He just make some graphics that is for a process that is happening inside the PLC and make it available in the HMI panel. Okay, so the layman can easily understand with the help of that graphics available. For example, a start switch. If we press the start switch, the particular boiler is going to be get in level of the water or level of the oil is going to be get inside the boiler, and that will be directly visible, make visible with the help of the graphics available, and the layman can easily understand, and we can teach them. If you see any indication like this, you just make this one to turn off. Like that, we can insist them to get operating the process control. Okay, so without the knowledge of a skilled engineer or a programmer, we can train a layman to control the particular operation that is happening inside the process plants. Okay, so for that, HMI is very much useful, and even we can also make some easy understanding what is exactly happening inside that particular program. Okay, so that is somewhat useful for us also. And signaling and listing. So what are all the terminals or how many inputs and outputs are used? All those details will be listed in your software. So if you are taking a particular input address or output address into your program, that will be included in your signals and listing panel in your software. Okay, so what are all the terminals we have used, what for the purpose we have used, everything we can make a note of it. And during your error debugging, this will be very much helpful for us. Okay, and last one is the real-time function. So some of the PLCs are available with a real-time clock. Okay, so for example, if you are going to design some project that is related to some traffic signal controller or any industry that is running under a shift basis, right? So we need to maintain the time to get synchronized with your machineries, right? So at that time, this real-time clock function will be very much useful. So particularly on a particular day, morning 6 o'clock, this particular machines need to be turned on. And after some 6 hours, they have to be halted for some 10 minutes or 20 minutes. Again, they have to be turned on for the next shift. Like that, we can make some sequential programming with the help of this real-time function that is available in your PLC. Okay, so PLCs are having some more number of options when you are going to select a particular module. Okay, so depending upon your application, you can select what module PLC we need. Okay, if your process is having some analog signals, means you have to select a PLC with analog processing. And if you are having your PLC to get synced with some time-based programming, time-based processes, means you have to select a PLC with real-time function like that. Okay, so these are some of the capabilities that a PLC can be able to do. Okay, so next thing, what is the features of PLC? So surely, since it is an electronic device, it has a reduced space and energy. It consumes only some 12 to 24 volt for its operation, right? And maintenance is also easy because no hardwired relays are used, only software relays are available, and it is economical. Economical in the sense its initial cost is somewhat higher, but there is no maintenance cost and it is having a greater life and reliability. Okay, so that overcomes the initial cost, right? And tremendous flexibility. This is the beautiful feature of a PLC. When you are going to upgrade your system process or any control logics means, then your PLC will pay the way for that. Okay, whereas other things will not have. Shorter project time, right? So the starting of your PLC commissioning and ending up with your connection with your output devices is having some lesser time when compared to your other hardware logics or dedicated control boards. Okay, so the project time is very small, shorter. Because your timing for doing your programming and getting communicated with your inputs and outputs through sensors, through switches, everything will be in a simple form. Okay, and achieving and documentation. So whatever the thing you are getting from your PLCs, that is your process output, your process input, and then your controller part and your programming part, everything can be documented in terms of soft copy, and you can make it use for some other projects, or you can use for verifying your particular project. Okay. So next thing is the constitutions of PLC, what a PLC will have. So this is a simple diagram that shows the constituents of PLC. Here it is having a central CPU, right, and then a program memory. So it is having a program memory and CPU, so that we will call it as a controller. Okay, so if it is not having any program memory here means, then it is called as a processor, right? Since it is having a on-chip memory, we are calling this one as a controller. That's why it is called as programmable logic controller, right? So it comes under controller category. And apart from this on-chip memory and CPU, here the PLC is having a specific modules called input module and output module. Okay, so this is what the PLC that is having in addition, right, when compared to our normal controllers, right? So a normal controller will have just direct terminals that is connected to your CPU directly. Okay, but here no direct connection with your input and output with your CPU. Okay, what for they have to make this one means the input module and output module will act as an isolator between this high voltage inputs and high voltage outputs with your low voltage CPU. Okay, so universally all the CPU ICs or controller ICs will work with 5 volt, we know, right? So if you are giving a 5 volt input through your input terminals means you can directly connect with your CPU. But in PLC, we are having a processing voltage of more than 12 volt to 24 volt. Okay, so since the 12 volt or 24 volt cannot be directly connected to your CPU pins, they are made through a input module. Similarly, a output module, right? So what this input module and output module will do, we will see now. See here, this is a detailed structure of the PLC, right? So your field input module will be always connected to your field inputs, right? So field inputs are nothing but your sensors, input switches, like that. Okay, whereas your output module is always connected to control elements. Control elements is nothing but a motor or a small DC motor or a actuator or a solenoid valve. Okay, so whatever the elements that are using in the industry for any control operation or actuators, they are coming under this control elements. Okay, so this field inputs are having some high voltage, that is 12 to 24 volt, right, and that are get connected to your input module in order to communicate your CPU. Okay, so what this input module will going to do, it will just convert this 24 volt or 12 volt input to a 5 volt signal. Okay, similarly, what this output module will do, whatever the output generated by this CPU with the 5 volt level, that will be converted into a 12 volt or 24 volt control element understandable voltage. Okay, so see here, this is what the input module. See, you have a 24 volt DC input device, right, and this input module will convert this 24 volt to 5 volt. Okay, and your CPU will receive either 5 volt or 0 volt, because when you are giving 24 volt, your 5 volt will be available in this terminal. Whereas when you are having some 0 volt, when you are having some 0 volt here, you will be having 0 volt in your CPU. So in other sense, we can think of that inside the CPU what it will be. Okay, because it is the 5 volt or 0 volt available at the terminal of the CPU, but inside the CPU, because CPU is a digital device, only it will be able to process some binaries, right? So when you are having 0 volt here, your binary value here is 0. And similarly, you are having 5 volt here, the binary value available inside the CPU will be 1. Okay, so in when you are seeing from the field input device, see here, when you are giving 24 volt at the input, your CPU will receive binary value 1. When you are giving 0 volt at your input, your CPU will receive a binary value 0. Okay, so in between that, you are having a conversion voltage called 24 to 5 volt here, right? The similar thing will be happening in your output module also. Okay, so your input module will have some additional functions that is performing here. See, signal conversion, and then signal isolation, right? And serial communication. Okay, so serial communication is nothing but through your voltage, we can communicate with your CPU, with your field device. Okay, and this is how your input module works for your CPU in order to access any input and output. See here, your input module will give a 24 volt field input signal to your CPU. So this will have a 5 volt here, and what this CPU will do, this 5 volt itself will not be directly reflected on your CPU pin. Okay, so CPU will have some 2 different chart available, binary chart available inside the CPU. One is PII, another one is PIQ. Okay, so in Siemens terminology, PII stands for process image input and PIQ stands for process image output. Okay, so Siemens always mention input with I and output with Q. Okay, whereas some other competitors like Allen Bradley and ABB, those fellows will use input with I and output with O. Okay, so this terms for mentioning the identifiers will get vary depending upon the manufacturers. Okay, so here in Siemens, I is for input and Q is for output. Okay, so while addressing, we have to give I for input and Q for output, right? So what the CPU will do with this PII and PIQ chart, these two are binary charts, right? So once you give any particular 24 volt through this field input device means, what the CPU will do, the CPU will go for scanning this PII chart frequently. Frequently in the sense, in terms of 0.02 milliseconds, it will scan this PII chart. Okay, this is a binary chart. I will show you how this binary chart in the later slides, right? So once the CPU scan for this, whether this binary value of any particular byte is get changed from 0 to 1. Okay, so what happens when you turn on a particular switch, that will be converted into a 5 volt using an input module, and that 5 volt is given as input to your CPU. That CPU 5 volt will be reflected as a binary value 1 inside your PII chart. Okay, so now the CPU comes and scans the PII chart. So there is a change in a binary value from 0 to 1, right? And it will pick that particular address and verify with your program memory. So program memory is also available in your CPU. So it will check with your program memory whether this particular input is used in your program. And if it is used in a program, means it will go for the line of sequence, right? That program in your line of program, what for this input is mentioned to turn on or turn off. Okay, so what it will do, again it will come back to your PIQ, and for example, if some other output is going to get turned on for that particular turn on of input means, it will come back to your PIQ and update the chart here. Update the chart means CPU will command a particular byte or bit value to change from 0 to 1. Okay, so once the byte value is changed, bit value is changed from 0 to 1, that will be reflected as a 5 volt in your output module, right? So your output module will convert that 5 volt to again 24 volt to your field output device. This is what the complete cycle that is happening inside a PLC. Okay, so now let us see one by one. This is what with the PII, and see here, this is what PIQ. So the CPU now go for the program and check whether your input is used for turning on any output. It will update the PIQ chart. Okay, so that will be reflected as a 5 volt output, and that 5 volt is again converted into 24 volt, and it is available to your PLC field devices. Okay, so this is process image output chart, right? So the CPU have communication with both PII and PIQ. Okay, and this all will happen in a fraction of seconds, that is millisecond, 0.02 milliseconds. Okay, right? So this is what your PII chart and PIQ chart. Okay, see, I am using a program, right? For that I have used the address I 1.3. So I stands for identifier, that is input, and 1.3 is nothing but bit and byte value. So byte value is 1 and bit value is 3 here. Okay, so see here, this is your byte chart, PII byte chart. So see here, byte 0, byte 1, byte 2. So 1.3 stands for byte 0, sorry, byte 1, bit 3, right? So this is the 0th bit, first, second, and third. So that's why it is made to 1 here. Okay, similarly, I 2.0 is get connected to your power supply, means, see, this is byte 2 and 2.0 means this is 0th bit. So second byte, 0th bit is turned on to 1. So now these two updated values are scanned by your CPU. Okay, the CPU will come into PII chart and scan this chart, right? And here we have two updated values changed from 0 to 1. So now it will go for user program. Okay, so now with the user program, what it will do, it will go for any updation in your output. So it will check for any updation in your output that is meant by the programmer. Then it will update in the PIQ chart. See here, there we have an update of if A that is I 1.3 is turned on, then Q 4.3 is to be turned on. So this is what the program that is done inside your PLC. Okay, so 4.3, it is the 4th byte and it is the 3rd bit, right? So it is get turned on now, and similarly 5.0 is get turned on. Okay, so this will be reflected as a voltage in your output module. Okay, so 1 it is get changed, means here we are having 5 volt in your digital output module, and output of your output module will be converting that 5 volt into again a 24 volt. Okay, so that is connected to your output terminals. What devices that are connected, that will be get turned on here. Okay, so this is what the simple process cycle that is happening inside the PLC. Okay, so if you have any input get turned on, CPU will come and scan. If any value is changed from 0 to 1, it will check with your user program whether that input or output inputs are used or not. If it is not used, it will keep mum. Okay, it will not take any action. It will not update your PIQ, right? If you are using that particular input to turn on or turn off any output, means it will make that particular process in your PIQ. Okay, so this is what happens here, right? So this is what a particular CPU scan cycle. See here. So in your PLC, you will have your programs to be done in OB. Okay, OB stands for organization block. So in organization block only we have make our programming to done through our either ladder logic or statement listing, like that. Okay, several methods are available, right? Once your programming is done, you can start the monitoring cycle time. Okay, once you make your PLC to run mode, it will start scanning your PII and PIQ values. Okay, so it will come for PII. If there is any update in your PII chart, it will go for your program, right? And the program, whatever you have done, it will be executed there, and the result of that particular program will be updated in your PIQ chart. Okay, and after that, it will go for again start scanning your PII for any other change. Okay, so this scanning cycle will happen within 0.02 milliseconds. Okay, then this time value will further get reduced depending upon the that is your provision of your PLC CPU. Okay, so some high level CPUs will have some reduced time values in terms of nanoseconds itself. Okay, so CPU with 0.02 milliseconds means, see here, even we can go for toggle the switches in a high frequent with the hands, it will be able to pick that value. Okay, we are not able to work for 0.02 We are not able to give any input within this 0.02 millisecond value. Okay, that is the thing, right? Even if you give, it will pick that input as a input value. Okay, and next we come to the addressing, how the PLC is going to get addressed here. So each manufacturer will define this identifier with their unique identification terms. Okay, so here Siemens uses I for input and Q for output. Okay, right? And bit memory bits can also be used here, and those will be termed as M, and T and C for timers and counters. But in latest PLCs that are coming under TIA portal means these PLCs are not having this timer T and C notations. Okay, so what PLC we are using here, we are not going to use with this T and C notations, right? Only we are going to make this data blocks as timer blocks. Okay, so timers and counters are declared as data blocks here. So no need to addressing of this timer and counter from the user side. Okay, it will automatically get addressed, right? Whereas this PII, PIQ and the memory bits, these things we need to address. Okay, so how we are going to address this? For example, if you are going to use the fourth terminal of the first byte, means we have to make this one as I1.4. But the thing is, you must have that much terminals in your PLC, that is hardware. Then only you can be able to use this particular input. For example, if you are using some 6 IO and 6 inputs and 4 output PLC, right? Only 6 inputs are there and 4 outputs are there. So what may be the starting address? All the PLCs must have the starting address as 0.0. That is 0th byte and 0th bit. Okay. So the first terminal of the input side, if you want to use, means you have to provide the addresses I 0.0. Like that. If you are having some 6 inputs, means you can use up to I 0.5. Okay, I 0.0 to I 0.5. So in that particular PLC, if you are addressing it as 1.0 or 1.2, means it is a meaningless. Okay, because the program will run, because software will have no limitation on your inputs, right? While you are downloading it to your hardware PLC, if the PLC is having that much number of terminals, then only you can be able to give an input through that particular address. Okay, so depending upon the hardware only, you have to give your address for your software, right? Because in your while programming, you must define how much input output terminals hardware PLC is going to have, right? Then only it will be we can make use of your inputs and outputs what you have mentioned in your software programming to get downloaded to your hardware PLC. Okay. Similarly, output might have some any address with 0.0 to some 256 bytes it will have. Okay. So this is for Siemens type PLC. Okay. Siemens will use identifier as I and Q. Then how about some other competitors like Allen-Bradley? See that they use IS identifier for input, and instead of 1.0, 1.4, they have used a colon with 1/4. This is the methodology how we are going to address for a Allen-Bradley type PLC for addressing a input. Okay. Similarly for output, see O, they have used O. Instead of Q, they use O and a colon and then 4/0. 4.0 can be addressed as 4/0. Okay, a little bit changed, but the logic is going to remain same for all the type of PLC. Okay, some notations and terms will be get changed depending upon the manufacturer, right? And I told that each addressing will start with 0th bit and 0th byte. That is the default for universally for all type of PLCs. Okay, so even it is Allen-Bradley, it will start with I colon 0/0. Okay, yeah, from that only we can able to start our initial input address. Okay. So these are some of the brands available in the market regarding your PLCs. See, this is a Siemens S7 1200 and Allen-Bradley. They will call it as ML. ML stands for Micrologics. Okay, Micrologics 1000, 1500, 1200 like that. And Schneider. Okay, this is from German. Schneider SRE 12B, that is 121BD. and ABB, American Brown Boveri, they have AC500. So these PLCs will range from a low number of inputs to high number of inputs. Okay, so depending upon that only the cost of that particular PLC also. Okay, so how to select a PLC? Next thing. So we know that what is PLC and how we are going to make use of the PLC. How to select a PLC before getting into your project. Okay, so first we must know whether you are going to use only digital inputs or our project will involve any analog values or not. Okay, once that is confirmed means then we can go for selection of the PLC depending upon our application. Okay, so number of inputs means how many digital inputs we need and how many analog inputs we need. Okay, so depending upon that we can select a module of the PLC. Similarly for output also, right? So next comes to the memory. So how much memory your program or your process is going to process like that. Okay, so if your programming is somewhat lengthier, means you have to select a PLC with a high memory value. Okay, so memory means that is nothing but the CPU, right? So the CPU memory, if you want to upgrade, means you have to make some more amount of cost for that. Okay, so that while you are upgrading your memory, all the PLC will have an upgrade in your CPU speed also. Okay, because once you want to upgrade your memory, surely your speed has to be upgraded, right? So these are the things we need to keep in mind once we are confirming to purchase a PLC in market for our particular process. Okay, and what are the additional functionalities? See, CPU capabilities, what are the things? So some system blocks and system function blocks available. So when you are comparing to our previous versions of your PLCs, the system function blocks are not available. Okay, so that's why we need to mention for a timer with a particular address and counter with a particular address, and that may have a mismatch, means your program will not be executed exactly. In order to avoid that, only the CPU capabilities are now enhanced to have system function blocks, and these predefined function blocks will have a certain functionalities loaded inside. So how a timer has to work, we don't define, right? It is a functionality already preloaded. We just drag and drop the timer and then make it working for our particular process. Okay, and the number of timers and counters and size of bit memory. Okay, so this comes under this memory also. So once you increase your memory, your number of counters and timers will also get increased. Okay, but in default, a basic PLC will have some 256 timers and counters. Okay, so I think it is more than enough for our small level or medium level process control operations. Okay, and is there any need for special function modules? See here, high speed counters. So what is the difference between this normal counter and high speed counter? Because when you are about to calculate some speed of a rotor shaft or a speed of a machine or anything, means you can't use that normal counter, because normal counter will count for a rising edge pulse which is happening at a particular frequency. Okay, if the frequency is get increased, means it will miss some of the pulses. Okay, so if you connect a Hall effect sensor in your shaft and make it available as a input to your counter, means it will miss some of the pulses when the rotor gets to a higher speed. Okay, so in order to avoid that, some of the PLCs will have a special function called as high speed counters. So high speed counters means it will able to pick the values even at kilohertz. Okay, even if you are making your inputs in kilohertz, it will pick each value individually. Okay, so your speed calculation or RPM calculation will be exactly the same as that what you have realized in your normal shaft that is rotating over there. Okay, and closed loop control. Whether you want any closed loop control, means you have to purchase a PLC with that particular option. Okay, a closed loop feedback module is there, and from that you can give a voltage or current feedback there, and that voltage and current feedback will be compared with your available reference value, and then the PLC will take decision according to that. Okay, and need for interface module, right? Interface module means if you want to have any additional thing, for example, if you want to include some HMI, means you have to define that because PLC is having a single Ethernet port or communication port that will be communicated either with your PLC, that is your PC, or some other device. Okay, so at that time, if you want to make communication between these three devices, for example, a HMI is there, a PLC is there, a PC is there, means with this single port, we can't go for any distributed communication. Okay, only a point-to-point communication will be established. So if you want to interface some additional module in your particular project, means you have to buy additional semantic net. Okay, a semantic net, what it will do, it will act as a sharing terminal which will be able to communicate two or more devices at a time. Okay, I will show you how a semantic net will be in the upcoming slides. Okay, and networking and communication capabilities also comes under this. Okay, so this is what the overview of the Siemens PLC available. So starting from, so not only Siemens, all the manufacturers will have a range of PLC modules like this. Okay, so the only thing is the cost, right? So once you enhance your module, then your cost will also be increased. That's the thing. Okay, so depending upon your size of industry or size of project, you have to select your PLC that is that you want to use. Okay, so starting from a logo PLC, this is what the basic PLC, which is having onboard key terminals. So we can either program with the help of these key terminals, or otherwise you can communicate through a programming cable. Okay, whereas this S7 1200 or 1500 family PLCs, this is also a low-end range PLC, which is used for small level processors, right? And here we are not having any display, right? In this type of PLCs, only we can able to communicate through a communication cable and directly to your software. Okay, and S7 300 and 400, these are somewhat PLCs that are mentioned for high-end processing. Okay, so this what this S7 to 300 and S7 1200 get variation means, this S7 1200 will be able to process up to some hundreds or 200 inputs and outputs. So the CPU has the capability of processing up to 100 or 200. Okay, if it is if the available onboard available terminals are 20 or 24 or 32, means additionally you can go for some 100 or 150 add-on units you can have. Okay, but when you are compared to S7 300, the single CPU can able to process up to 1000 IOs. That is the thing. Okay, so think about the capability of the CPU. The CPU can be able to process up to 200, means this will have some 5 times more capability. So what about the cost? So this will cost around 25,000, means this will cost around some 3.5 lakhs. That is the thing. Okay, so but in terms of industry, when you are going to process some thousands of input and output, this 3.5 lakhs is not that much bigger cost, because it is one-time investment that the industry is going to pay for that. And once you let the PLC to run for a particular process, means it will take care. Okay, it will reduce some for 10 to 20 laymen that are those who are working on that particular process, right? So where the running cost is very much less when compared to this implementation cost. Okay. And this is the summer software overview, what are the softwares used. So I will just to focus on this S7 1200 and 1500. We have limited time, right? So these are some of the softwares available in market, and each software is having a license, right? So without license, we can't go for any programming. Okay, even if we able to program with like unlicensed version, means we can't able to download. Okay, so here we are going to use a software called TIA portal, TIA, Totally Integrated Automation, TIA, right? So the TIA stands for Totally Integrated Automation. Why we call it as a Totally Integrated Automation means this single software can be able as to communicate with a PLC, a HMI, and then a PC. Okay, so this is what the advantage of the previous version of softwares, right? So see here, this S7 Microwin is a software mentioned only for communicating with a PLC. Okay, we can't able to communicate with a HMI. For HMI, we need a separate software called WinCC in the previous version, previous module of PLC. And once you program with WinCC and with this S7 Microwin, we have to interlink those two software tags separately. Okay, that is an additional work, right? But in your TIA portal, we can able to migrate in the same software window to a PLC and then a HMI and even a drive. Okay, a AC or DC drive, that is get connected, we can migrate inside the software itself. Okay. So let us begin with a small simple programming for you. So I'm opening the TIA portal version 15. So it's actually a licensed version, right? So actually your software will have some two different view. One is the portal view. See here, this is a portal view and then a project view. Okay. So now we are in a portal view, right? So in portal view only we can make our first steps of your programming. See, I'm going to create a project. So TRP webinar. I'm just creating a new project called TRP webinar. See, once the project is get created, it will ask some additional steps to identify what you are going to do with this particular software. See here, a new project is get created. Okay, next it will migrate to first steps, right? So in the first steps, see here, these are the steps we can do. Whether you can configure a device or write a PLC program directly, or configure technology objects, right? And parameterize a drive, anything, right? And configure a HMI. But since it is an initial step, I am just going to configure a device. So I just click configure a device and add a new device. Okay, because I'm not having any device to get added to this particular project. Okay, so whether you are going to add a controller or a HMI or additional PC or a drive. So these are the options available for us to get communicated through this software. Okay, so initially I'm going to add a controller. So in controller means what type of controller? See, several modules of controller are available. So this is S7 1200, this is S7 500, 1500 and 300, 400. These are several PLC modules available in this particular software. Okay, so whatever the thing I have selected, that is related to my software only. Okay, so if you know what is exactly in your hardware, then you have to select through this CPU. Okay, because all the CPU in your hardware PLC will have a numbers printed on that. Okay, which type of module? See, in my CPU, it is printed as CPU 1214C AC DC relay. Okay, so I have to select what PLC I am having in my hardware, and I have to select it in my software also. See, 1214C AC DC relay. This is what the CPU I am having in my hardware. And in that I am having some 3 different modules, right? So which module you are having exactly, that will be defined by this MLFB number. Okay, so this MLFB stands for a German wording, that is Maschinen Lesbare Fabricator by Xinjiang. That is what MLFB. Okay, that means in our colloquial we can call it as a machine readable code or machine readable number. Okay, or part number, anything you can. Okay, so this is what the MLFB that is printed in the side of my hardware PLC. So I have selected it, and if you want to add this to your software, means it will add this particular software PLC to your TIA portal software. Okay, so until now we have selected only the software, right? Once you are about to download your program to your hardware, at that time your software will check for that MLFB numbers. Okay, whether your software PLC selected and your hardware PLC available or having the same MLFB. If it is not, means it will not allow you to download that particular program and make an error called as hardware or target device not matched, like that. Okay, so now the software PLCs get added to your programming, that is your software window. So here additional slots are available. These are the additional slots available for adding your add-on units if you want. Okay, so the add-on units are available in this particular hardware catalog, right, in the right side of your project window. Okay, so now the TIA portal is migrated as to this project view. Okay, see in the presentation, see here, this is the portal view and this is what the project view. Okay, so now we are in project view. Okay, so in project view you have several windows available. Depending upon the selection of your devices, the windows will get varied. Okay, if I click on this PLC, see here, double click means window from the bottom it will pop out. Okay, that is, it is called as inspector window, right? So inspector window means inspecting. You are inspecting this PLC means the details that is regarding this PLC will be listed here. See, this is the general details. The PLC is named with the PLC_1. It will automatically naming it. And profinet means what is the Ethernet address available for that. So it is 192.168.0.1. It is available here. If you want to make a change, you can make a change. Okay, but the thing is, the same address is to be available in your hardware PLC also. Okay, and what about digital I/O? See here, we have DI14 and DQ10. That means totally it is a I/O 24 I/O PLC. That is 14 for input and 10 for output. So 14 means starting address will be I0.0 and ending address will be I0.5, I1.5. Okay, so I0.0, 0.1, 0.2 up to 0.7, 8 terminals, and then I1.0 to 1.5. That is around 6 terminals. So 8 plus 6, we have 14. Similarly, for output 10, that means Q0.0 to 0.7, 8 terminals, and then Q1.0, 1.1, 2 terminals. Okay. So if you select a PLC with this 14 input and 10 output lanes, in your program, you will be able to use only that 14 inputs and output addresses. Apart from that, if you are using some I2.0, I2.1 means the program will run inside your software. No problem, it will not showing any error or like that. Once you download it, you can't be able to give an input to that particular terminal I2.0 because your hardware PLC is only having the input as I1.5. Okay, that is the last highest number of byte input value you are having, 1.5. So you are using 2.0 means you are not having any terminal in your hardware. That is the meaning. Okay, and when you are coming to your project tree, this is what the project tree. Here you can able to find the program block. So here only you are going to do your program. Okay, so once I open the program block, it will ask you for two things. Either you can go for a new block or a opening an available block. So I am just opening an available block here. Okay, so let us go with the simple programming for your understanding. So this is what the programming window, and the programming language what we are going to use here is nothing but a ladder logic. So why we call it as a ladder logic? We can also call it as relay ladder logic. Okay, because why we are calling it as a relay ladder logic means this programming will surely work on the principle of relay concept. Okay, so we are going to use open contact, close contact, coils and timers and counters that are connected to that coil and contact, like that. It will work on the principle of a relay concept, since this program is called as a relay logic, ladder logic. Okay, and why the name ladder? See here we have their left side a line with 24 volt plus, and then right side a small hyphen you're having. Okay, I don't know whether you're able to see this. I'll just zoom this one. See here in the left side, this is the left side, you are having a 24 volt positive, and the right side you are having a 24 volt negative line. Okay, and you are connecting your components in between this plus and minus. Okay, so once you increase the number of lines, it will look like a ladder. Okay, so this 24 volt positive will act as the handle, one of the side of the handle of your ladder, and 24 volt minus will act as another handle of your ladder, and this line of programs will act as the steps of a ladder. Okay, so let us go for a simple program. See, I am going to take a normally open contact, right? So where you can get this contact and coils, you can also get it from the instructions. Okay, so these instructions will be available in the right side of your software, right? Whatever the instruction sets we want to use, you can drag and leave here. Okay, but I am having it in my favorites block, so that I can take it out here. Okay, and I have connected a contact here, and this contact is connected to a coil. Okay, so a 24 volt positive, a contact, open contact, and then a coil, and then a 24 volt negative term. Okay, so this coil is nothing but output, and this contact is nothing but input. Okay, so what we need to do, we need to give the addressing for this. Okay, 1 second. Same network problem again. 1 minute, sorry. Wait for 1 minute. I have a hang in my software. It is a very huge software. Wait for a minute. If you are having any doubt in the session we have, we can now discuss until the system gets restarted.
Is it possible to share PPT, sir, please?
Yes, sure. You share.
Okay, thank you, Langon, sir. Thank you, thank you.
Sir? Sir?
Yes. Tony, சொல்லுங்க. Join ஆயிடுச்சு.
Able to
Yeah. Are you able to view the slide?
Yes, sir.
Yeah. Thank you. So next 10 minutes I will close the session. Okay.
Yes, sir.
Right? Yeah. So here we have connected a open contact and then a coil. Okay. So between our positive and negative lines of our program. Okay. So I need to give an address for this input and then address for this particular output. Okay. So surely I will start with I0.0 for my initial input and then Q0.0 for my output coil. Okay. So once I declare this input and output with my software, so I have to check whether these two addresses are available in my hardware PLC. Okay. So surely I am using a 0th byte and 0th bit means basic PLC will have that one. Okay. Even it is having some 4 input terminal and 2 output terminal, which will include this 0.0 terminals. Okay. So now before communicating with this PLC software to my hardware, I have to compile this particular programming whether it is correct or not. So in the top of my taskbar, I'm having compiling. See, once you compile this, it will show you whether it is having any error in your logic or not. Okay, so simply it is having a simple connection, a simple a toggle switch which is get connected to a coil. Okay, so let us check this one how it will be working with your hardware. For that, I'm going to download this to my PLC. See here, I'm downloading this. So next to my compilation, I'm having a download tab. So I'm clicking that download tab. Now the PLC software will check for a hardware in that particular IP address. Okay, so already I have shown that the PLC software will have an IP address of 192.168.0.1. Okay, so if you are having the same IP address available in your hardware PLC, then it will establish a connection between your software and then a hardware. Okay, so see here, this is what the software that is going to search for that particular IP 0.1. Okay, so now I am going to give start search. It will search for the hardware. See, once it is available, it will be listed here. See here. So we have a indication that it will find a PLC and then a HMI in the hardware, and it is attempting to connect with the device with 192.168.0.1. Okay. So once it is identified, see, it will show you if there is a PLC available at that particular address. This is not the hardware PLC. So now, if your software PLC device type and then your hardware PLC device type is not matching, means then you can't able to download. Okay, so that I have confirmed with my hardware PLC before selecting my software PLC with this CPU type. Okay, CPU 1214C AC/DC relay like that. Okay, so now I am going to load this one. I am loading this particular program to my hardware PLC. It will ask for a temporary IP. Yeah, I am providing that. Now again it will go for a compilation, and I'm going to stop all and load the program. If already something is running, means it will stop the CPU and then download our program. So now the PLC downloaded, the program is downloaded to your hardware PLC. Okay, so here I'm having a hardware kit so that I can easily verify it here. So I have turned on my toggle switch, the output Q0.0 which is connected to an LED get turned on here. Okay, but if you want to verify it through your program, that is through your online board, means you can have an option called online monitoring, right? See here, now the power supply enables are made as green and blue. So those are enabled will be marked as green, and those are not enabled will be marked as dotted lines with blue. Okay, so once I turn on the switch in my hardware PLC I0.0, see here, it turned on Q0.0. Okay, so here in the trainer kit, Q0.0 is connected to a LED. So I will show you how the trainer kit is looking like. So this is how the trainer kit what I am having here. Okay, this is a DI1410IO. See, this is what the toggle switch. You can able to see this one. These are the set of toggle switches available, and these are the LEDs available for my output. So you can able to view the address. See, DI0.0, I0.1, 0.2, 0.3, like that up to 0.7. Okay, so totally 8 toggle switches are available in the first line. And then what about the number of IO inputs? 14 inputs you are having. So 8 plus 6. So 6 switches are available in the next line, I1.0 to 1.5. Okay, similarly, 10 outputs are available in my PLC. So those 10 outputs are connected to LEDs. Okay, so this will be useful for the students to verify whether the output is exactly get turned on or turned off depending upon the program. Okay, so in my trainer kit now, I have turned on this switch I0.0. So that will give an input voltage to this particular contact, right? And that will check with my program So it will, the PII, CPU, what it will do, it will come and check with my program. This I0.0 is directly connected to Q0.0. Okay, so what it will do, it will go for the PIQ chart and update the byte value of Q0.0 to 1. So that will be reflected as 5 volt from the CPU and 12 volt or 24 volt from your output body. So that is connected to LED here, and this 0.0 LED is now flowing in my hardware PLC. Okay, so let us try with one simple additional logic. So now what I am going to do, I am going offline again, right? I am going to include a timer. See, a on delay timer I am going to include in between this input and output. Okay, so I already told you that no need to give any address for these timers. Okay, because in previous versions of your software we need to give address for your timers and counters, but in TIA portal we are not having any options to include the addressing of a particular timer. It will be automatically declaring its addresses as IEC timer. Okay, right? So now a timer, on delay timer, is introduced in between my input and output. So see here, I am going to give a delay of 5 seconds. So if I type 5 in my preset time, means it will take it as 5 milliseconds. So what about the base value available here? It is in milliseconds. So if you want to enable your timer for 5 seconds, means then you can give it as 5,000. Okay, so I am giving it as 5,000 now, right? And I am downloading this. Any change in your program you have done, you have to download it immediately to your PLC. Okay, then only it will be reflected. Yeah, now it is get downloaded. So I am going to online. See here, since the switch is in on condition, it is directly giving output. So now what it will do, on delay timer, it will provide a delay for 5 seconds, and then only it will get your output to get connected to the input. Okay, so this on delay timer, see here, I am turning on the input, so it will run for 5 seconds. See, the accumulator value is running for 5 seconds. After 5 seconds, it will get your timer to your output Q0.0 to get turned on. Okay, similarly, there are several types of timers available: off delay timer, retentive on delay timer, pulse timer, like that. Okay, so with this use of this timer block, counter blocks, and input and output contacts and coils, we can make our programming for any process control of systems. Okay, so depending upon your project, the length of your programming, and then the number of components that are utilized in this particular ladder window will get vary. Okay, and when you want to introduce some additional branches, you can use this additional subsequent branch operations and close operations in your programming. See here, if you want to include additional branch over here, you can directly include it here. See, I have to provide 0.1. Next output means, see here, one of your output is get turned on after 5 seconds, and one of your output is get turned on immediately. Okay, so I'll just show you. See here, when I about to turn on my I0.0 high, my Q0.1 is turned on immediately, whereas Q0.0 is turned on after 5 seconds. Okay, right? So you can change the places also. You can connect it here, means both the inputs, both the outputs will get turned on after 5 seconds. Okay, see, both the outputs will going to get turned on after 5 seconds. Right. So in this way, you can define your programming with the help of this contacts and coils available. Okay, so there are several instructions left over in this particular software. Okay, so when you want to add some number of inputs, then you can use these arithmetic functions, right? And if you want to compare some two different input and outputs, means you can use these compare blocks, right? And counters and move operation, right? And then conversion. So when you are using analog processing, we can use this conversion operations to get run for our particular task and everything. Okay, So whatever the things we are having in our normal microprocessor and microcontroller, all the commands will be executed in your PLC also. Okay, the thing is how we are going to integrating your components in a particular ladder window like that. Okay, so there may be some errors occurring when you are going for some initial programming or initial steps of programming in terms of addressing the input and output like that. Okay, but when you are continuously working on this particular the softwares and the different modules of PLCs, then we can have a clear understanding how to mention the input and how to mention the output, and how we are going to integrating the input and output in your ladder window like that. Okay, so continuous homework on this particular softwares and hardwares will make us to well knowledge or well equipped in this particular area. Okay, so this is a simple wiring diagram of your PLC, right? So this is what the PLC available here in your hardware. That is S7 1200 PLC. So it is having input side, and this is what the output side, and it is having an analog channel. Okay, it is having only analog input channel. This 1214C is having analog input channel, and you can able to process from two different analog inputs here. Okay, so analog means what we can do, we can either have a temperature sensor or pressure sensor or level or flow. Any analog processing can be monitored or controlled through our analog channel through that particular sensor outputs. Okay, the sensor outputs might be of 2 or 3 types. That may be voltage output, that is a current output like that. Okay, so voltage output sensor means we have to make your analog input channel with voltage variation. Okay, or with voltage calibration, right? If you are going to have an analog sensor with current output, means you have to select a PLC with current input analog channel. Okay, then only the PLC will be able to process. Okay, if the available sensed value is in understandable form for that particular PLC, then it will process that. Okay, so show you what is semantic net. So semantic net is nothing but this one. This is an additional module available in your PLC. Okay, so you can have this one is the semantic net. Right, this is what your PLC, and this is what the semantic net. See here, we have connected some 2 to 3 devices at a time through your software. Okay, for that only the semantic net is used. Okay, so what the semantic net will do means, see, I can have a PLC and then a semantic HMI and then a drive and then a PC. All these 4 to be communicated from a single software. Okay, single software is nothing but my TRPEC. Totally integrated automation software. Okay, so in this way we can have a sharing between the tag values and parameters what we have picked from PLC. You can share that value to HMI, or sometimes the decisions will be made from HMI to the PLC like that. Okay, so this semantic net plays a vital role when you are having 2 or more devices to get communicated for a single process plant. Okay. So I think this is somewhat enough for us to have a clear understanding on what is PLC and what is happening inside a PLC. Okay. So is there any doubts?
Addition, if you have any doubts, please raise in the chat box.
Okay.
Okay, sir. Sir, Arul Prasanna, sir. The thing will be shared in YouTube. They have asked doubts, sir.
Okay.
Sir, what is some of the questions are, yes, sir?
Yeah.
Sir. Okay, sir. Right. Sir, now one participant, as Mr. Dr.M.Arul has been asked, in which mainstream of applications the Siemens have been implemented? This is
in any type. I will answer him. In any type of process control industries, PLC is the basic thing. So, what is first process control industries? Any product, that is any industry that is converting a raw material into a particular product. Okay, a simple raw material into a particular product means that is called as a process industry. So all the process industries nowadays are using PLC. Okay, that is sure, right? In addition, they are going for some upgradation in their methodologies and in order to reduce the layman work and manufacturing cost, they have go for some additional technologies called as SCADA, like that. Okay, they get just upgraded, because even if you are using SCADA and DCS, distributor control system, everything will include this PLC as one of the components, because all the decisions made by the made for the particular input and output that are received from the sensors and actuators are processed through a PLC only. That is the thing. Okay, because SCADA is an additional software stream that is associated with the PLC, which will monitor the happenings inside the PLC input and outputs, and it will make your controller, or who is going to be the user programmer, to understand what is happening inside. Okay, so process industry means surely there will be a PLC. So this is a major application where you can find our PLCs. Okay, so you can think of any process industry, right? Either you can have a soap manufacturing, car manufacturing, chips manufacturing, beverages, any process industry that is going to convert a raw material into a product will use a PLC. This is damn sure. Yeah. Any other doubts?
Next participant, Wilmur asked one question. How does DCS differentiate from PLC?
Yeah, DCS is, for example, you are having a process industry for oil and gas. Okay, process industry for oil and gas. What they will do, they will just go for picking up the raw oil and then go for refining process and then make it as a refined one. Okay, so in that oil and gas or any process plants or instrumentation plant, there will be some steps for going for that refining. Okay, so each step is having an individual project or individual process, right? So refining involves some sedimentation process like that, and extraction involves some extraction of the impurities and finding of the impurities, or removal of ion particles inside the oil, like that. Okay, so each will have an individual set of process, and for example, from front to end, we are having some 5 stage of process means. If you are seeing that 5 stage of process individually, then it is a process control. Okay, when you are combining all these 5 stage of process into a single form, then it is called as a DCS. Okay, so a single PLC will not able to monitor all these 5. Okay, so if we are implementing some 5 different PLC and 5 different SCADA system for this particular 5 different process happening in the refining plant, and if all the things are accumulated inside a single window, means that is called as DCS. Okay, so this DCS will have a monitoring of all these 5 individual plants and can able to make decision, or can able to make any on or off commands at any stage of that particular processes. Okay, this is what DCS, right? DCS is it's a high level. Okay.
Sir, another question from Subramanian J. Difference between Omron and Siemens, which one is best to our country?
Cost-wise, Omron is somewhat lesser than compared to Siemens, because Siemens is somewhat a higher cost when you even purchase a small basic level PLC. I will tell you a simple thing. Siemens with a simple 10 IOs, that is 6 plus 4, 6 input and 4 output, will cost around 25,000. Okay, and without any analog means you can buy up to 15,000. Whereas when you are going for an Omron, it will cost around 7 to 8,000 only. There are some other manufacturers available called Delta Electronics. They are leading in PLCs, and they are manufacturing even with 6,000 rupees also. Okay, so those who are trying to do some projects in PLC or automation related area, small projects related to that, if you are not able to purchase for some 15 to 25,000 means you can go for this low range, low cost PLC. So working is same. Okay, but the thing is the brand is different. Okay, so the comfortability in your programming will also have some difficulties. Okay, when you are going for the Siemens type PLCs, the programming and the software available is somewhat user friendly one. Okay, when you are going for some other manufacturers, their programming windows and software availabilities are not that much. That is the variation between these manufacturers. Okay, but in Gulf, when you are seeing in Gulf, these PLCs are used in a wide variety there, and depending upon the that is the managerial people available there, they will purchase the PLC. If the managerial people depends on some European countries, means surely he will go for Siemens type PLC. Okay, because Siemens is German made, right? So they recommend only Siemens type PLC. If the managerial people is from Western, means he will surely go for an Allen Bradley or like that. Okay, so this is what the difference between the manufacturers and how they are selecting for that particular plan, right?
Sir, one more question. Which company PLC is widely used, and what communication protocol used between PLC and field devices?
Yeah, mostly used PLC or widely used PLC is nothing but Siemens. Okay, in worldwide, they are the leading manufacturers in this automation sector, and next to that is Allen Bradley. Okay, these two are equal competitors, no difference between them, but Siemens is somewhat a little bit higher, one step forward. Okay, so whatever the PLC module they have designed in Siemens, they have released a product in January, means surely Allen Bradley will release in February. That is the competition happening between Allen Bradley and Siemens. Okay, and the protocol used for majority types of PLC is nothing but a Profinet protocol. Okay, so Profinet and or Profibus you can call it as, right? So when more number of PLCs are get communicated, we can go for Profibus. Then less number of PLCs, we can make it as a Profinet. Okay, a point-to-point communication between your PC and your PLC. Okay, so Profinet, Profibus, and depending upon the manufacturer, the communication will also get varied, because if you are having an industry with a Modbus communication, means you can have a PLC available with Modbus also. Okay, that is the thing. So depending upon the communication also, you have to select your PLC. That is what mentioned in the selection criteria. So you have to select your PLC depending upon the communication protocol also. Okay, if your industry is following some Modbus communication or some other communication, and you are purchasing a Profinet or a DP, right, PN or DP communication PLC, means you can't able to integrate that one at the time of your commissioning. Okay, so you have to make sure what type of communication that is available in your industry or in your plant, and you have to go for a particular type of protocol PLC from the market. Okay, so sometimes Siemens is not having a Modbus communication PLC, means you can go for some other manufacturer, right? That is the thing. Any other?
So the last question, sir, how to download TAA V15 software? It's free or paid software?
Surely it is a paid software, but there are cracked versions available online. But even though you purchased, you have downloaded a cracked version, it will not that much working with your hardware. Okay, because this is a hardware software integrated thing. Okay, so once you have a pirated software, but anyway you have to buy a genuine hardware. That is the thing, because with software alone we can't do anything. Okay, even you can make the program and we can view the program or compile the program, but we can't download it. Once you download the software program to your PLC, then only it will be useful. Okay, then only you can be able to see what is happening, our project is running exactly correct or not, we can understand. Okay, so buying a PLC a genuine PLC, and then a software is the only thing we need to do. Okay.
Sir, shall we wind up the session, sir?
Yeah.
Okay. Thank you for your wonderful session, sir. Now the time for vote of thanks. I request Mrs. Kriba ma'am, Assistant Professor, Department of Electrical and Electronics Engineering, to deliver the vote of thanks.
கேக்குமா மேம்? ஓகே மேம். இதை பிடிக்கணுமா மேம்? Good afternoon all. On behalf of SRM TRPEC, I am here to present vote of thanks for today's workshop. I would like to thank our today's chief guest, Dr.M.Arul Prasanna, Associate Professor, Department of EEE, PSNA CET, for enlightening us with his knowledge. Today's workshop was full of knowledge and he shared many aspects on PLC. It gave deep insight into the topic and also revealed some basic facts on role of control systems in automation. And also I am sure that the precious knowledge shared by him will definitely guide us in future. Once again, I would like to thank Dr.M.Arul Prasanna for taking out time from his busy schedule and enlightening us with this knowledge. Thank you so much, sir. Thank you, sir. I would also like to thank our principal, sir, Dr. B. Ganesh Babu, for permitting us to organize workshops and giving continuous guidance. Thank you, sir. I would like to thank our HOD, Dr. P. Ilangovan, sir, for guiding and providing continuous support for making this workshop successful. Thank you, sir. And also, I would like to thank our faculty members for their kind support. Finally, I would like to thank all our participants for patience listening and made this workshop success. Thank you all. Feedback link.
Thank you, ma'am. Thank you, sir. Dear participants, thank you for your spending time in this workshop. And the feedback link is posted in the chat box.
The feedback link has been posted in the chat box. You can make use of it. Similarly, we have also posted the same feedback link in a YouTube link also. I thank personally all the participants for your best making. Thank you for your patience for this time, sir. I personally thank Dr. Arul Prasanna, sir, for accepting our request and making us and revealing us the PSNA Siemens theory with us. And I think this is a very short time for you, sir. I'm sorry I could not give you a day.
Thank you.
It was really very nice and wonderful session, sir. Very wonderful session. Thank you very much, sir. I personally thank you very much, sir.
Thank you so much.
Sir, Arul sir, thank you very much for your wonderful session, sir. Thanks a lot,
Thank you, sir.
Thank you very much.
Thanks for the opportunity.
Thank you very much, sir.
Sure, sir.
much.